Welcome back to another one, and we're doing another two pointers. Another two pointers because I actually enjoy two pointers a lot. I found that it's a very fun way to think about things. So we just did two sum to input array is sorted, and let's go into three sum. And we will be given an integer array nums, returning the triplets such that I is not equal to j, I is not equal to k, and j is not equal to k, and nums I plus nums j plus nums k equals 0. Notice that solution set must not contain duplicate triplets. So we're given some negative integers, some positive integers, and some 0. And we can be given when we're supposed to find all the triplets within this array that returns 0 when you add them together. Nums0, nums1, nums2 is this, and we just return the values. We don't have to worry about the positions like how we did with the two sum input array sorted question. We are looking for the element values. We have to take care of some things where we have an output array of nothing if there are no possible sums of 0, and we can output all zeros if there are all zeros. So we need to somehow create a pointer because I want to follow that convention that I messed up in the last one with the two sum 2 input array. I don't want to use a dictionary. I want to use pointers to determine where the pairs are. So the first thing we can do is take nums and sort it. I'm not quite sure why this is necessary quite yet, but we'll figure that out. And we can look at result. We can have a resulting array that we will add to and print at the end of the method. So we'll take a for loop to go through the range of the length of the nums array that we're given. And if nums at the particular index is greater than 0, we can break out of the loop. And we want to do this because, let's see, why would we want to do this? Why would we want to do this? Tell me that. Nums index greater than 0, we would break. Break it. It's like we're just skipping to the next one. But if we can look at this nums index in the context of everything else, if index is greater than 0 and the nums at index is equal to nums at index minus 1, we can continue. So this just skips to the next one. This allows us to continue through to the rest of this for loop. So now this is where we create our pointers. So we have our left pointer and we have our right pointer. where our left pointer will be the index plus 1, and the length of the index, or at the length of nums, which is the input array, minus 1. This is a pretty common convention that I'm starting to recognize more, where we have left at the beginning and right at the end. And there's always 2. There's never more than 2. Because that makes sense. It's 2 pointers. That's the that's what it tells you in the name of the concept. So while left is less than right, this is also another common convention where as soon as the pointers pass by each other, we can return something. You know, in this case, before we return anything or append anything, we're going to do all of the checking to see what matches up based on the result we're looking for, the patterns that we're looking for. And in this case, we're going to look if nums at the leftmost point plus the nums at the rightmost point is greater than 0 minus nums at the index. And if this is the case, then we can iterate the leftmost pointer by 1, by adding 1 to itself, because it starts off as, well, it starts off as 1 because index starts off as 0 plus 1 is 1 for left, and then we add 1 to it, so it becomes, 1 to 2 to 3, etc. So long as, if this isn't true, if it's not greater than 0 minus nums of index, we can use an else if statement to check if nums of the left side and nums of the right side is greater than 0 minus nums of the index. So what this is doing is that if this continues on, if this happens, then it'll iterate 1 to the left. Regardless, it's going to check if we can iterate, we can iterate the leftmost pointer 1 to the right. And then regardless, it'll check if the sum is greater than 0, and what's going to happen is it's going to iterate the rightmost pointer to the left. And as a result, we are going to append the 3 values of nums at the index, nums at the leftmost pointer, and what do you think, nums at the rightmost pointer? And to go through all the values, because we successfully found a triplet that adds up to 0, we can move the leftmost pointer to the right by 1 and the rightmost pointer by the left, or the rightmost pointer to the left by 1. Then we can check if the leftmost pointer is equal to the leftmost pointer minus 1 and left is less than right to iterate the leftmost pointer by 1. So this is checking the leftmost pointer to the right by 1. So this is checking if the pairs are, or I guess this determines if the pairs are either duplicates or smaller than the target. So I'm trying to wrap my brain around all of this right here. So let me try to explain it to myself real quick. But by the end of this entire for loop, if it makes it all the way to the end, then we can return the result because it will have the triplets that exist within each input array within the output array. So let me break this down once more. We have for the index in the range of length nums, so it starts off as 0. And if nums of index is greater than 0, you go to the next one. If index is greater than 0, and nums of index is greater than or is equal to nums of index minus 1, then we can continue. If this is not true, then what happens? I don't know. What happens after this? I need a better explanation. I can't really... It's hard for me to wrap my brain around anything beyond the 2 pointers. It's like as soon as that third pointer or that third value where you're looking for... where you're comparing that third element, these if statements confuse me, and then the while loop where it's taking everything into account with index and the 2 pointers that are moving to the left and right, I get lost here. So let me ask my friend. So I understand we have a list of numbers called nums, and we look at each number one by one, which is 4, oh, I like that. 4 index in range. If the number is bigger than 0, we can stop looking at the numbers. If we've seen the same number as before, which is this one, if nums index equals nums index minus 1, okay, that makes sense. Then we can look at the next number. Then this is where the 2 pointers get introduced, left and right, where left starts right after the current number and right starts at the end of the list. So I don't understand the reasoning why you do this. So let me get that clear first before going to the next, number 6. So this is the explanation I'm looking for. By placing the left pointer right after the current number and placing the right pointer at the end of the list, we can search for pairs of numbers that meet the condition without having to check all possible pairs, which would take much longer. So as we move the left and right pointers toward each other based on the condition, their sum being smaller, equal, or greater than the negative of the current number, we can effectively search for the required pairs in a faster and more efficient manner. So this is my interpretation right now. We have our array, right? Our list of numbers. And we're pointing at the first one. And then we move the pointers inwards from the left side and the right side. And if none of those match up to the... If none of those match up to the 0, then we can iterate we can iterate that first one to the next value. And then we can use the pointers again to look inwards and outwards simultaneously, going again to iterate the first one to the next value, and then using the pointers to look in from the left and right again to see where the required pairs are. So then what we do is we keep checking the numbers at the left and right pointers until they meet. If the sum of the numbers at the left and right pointers is smaller than the negative of the current number, we move the left pointer one step to the right. So there's even conditionals to move the left and right pointers inwards towards each other. So if the sum of the numbers at the left and right pointers is bigger than the negative of the current number, we move the right pointer one step to the left. Interesting. So I'm having a hard time again to wrap my brain around these conditionals to move the pointers. But I do understand that you can look at the sum of the numbers at the left and right pointers being equal to the negative of the current pointer to find the members that add up to 0. That kind of makes sense. And then, you move the left and right pointers in towards each other again. If the number on the left is the same as the other one, we just check, we skip it, and move the left pointer one more step to the right. Then after looking at all the numbers in the list, we return the result list with all the groups of 3 numbers that add up to 0. There's something missing from this where you move the current number to the right. So I'm going to look at the video solution because there's a few things that make this more complicated than the two-sum
3-sum, the sequel to the popular question 2-sum. So before you solve this question, the first thing you should do is make sure that you've solved 2-sum, which is the most popular question on LeetCode, so you've probably solved it or at least seen it before. I also recommend solving 2-sum 2, which is basically 2-sum except the input array is sorted. A lot of people skip this question. I think that's what makes 3-sum a little harder because they don't solve this one first. If you solve 2-sum and 2-sum 2, this question 3-sum is pretty straightforward in my opinion. But okay, let's get into the question. So we're given an input array of n integers as per usual. This array though can have duplicates as we can see in the example, right? 2 negative 1s in this case. Now what we want to do is find 3 numbers of this array, so A, B, and C, and we want them to sum to 0. So in the example, there were 2 elements, or 2 triplets that summed to the total 0. Now one problem is that we cannot have duplicates in our solution. So we're going to have to keep that in the back of our minds. So let's just start the most brute force way. We see that we need 3 numbers, so why not just have a triple loop, right? Just get every single combination of 3 numbers. That's probably the first thing you're going to try, right? So let's say our first number is -3. This is our A. So we're going to try each of these numbers for B, right? This could be a B, this could be a B, this could be a B, this could be a B. This last one can't be a B because we need at least one number to come after it so that it's a C. Now, if we did that with our triple loop, we would find that there is one such combination starting with -3 that will sum to 0. If we take 1 as our B and we take 2 as our C
3
value,
loops,
because
but it would
then
be
we'll have
so
-3
slow.
plus 1 plus 2, that's obviously 0. So to our solution set, we can say, okay, there's a -3, a 1, and a 2. So now when we move, we can consider this as our first element, right? But eventually we'll see that we go through the entire thing and we don't find anything that can be added to 3 that'll give us a sum of 0. We'll do the same for this one and there isn't anything. Now we get to a -3 again though, because remember there are duplicates in this array. So now we're saying again that we're going to put -3 in this first spot. Now this is a recipe for finding duplicates. This is not good. And we'll see in this example, that's exactly what's going to happen. We'll take this as our B.
So that's interesting how they mentioned duplicates. That's like something I didn't wrap my brain around when I looked at the solution or tried to solve it initially. So the importance I need to figure out some kind of importance to not contain duplicates, or how to conceptualize that concretely in my mind.
B, we'll take this as our C. Again, we find -3 plus 1 plus 2 sums to 0.
So when you use a loop like that, you have -3 once and then -3 again. I don't know why. Oh wait, this would only have one solution, or one triplicate of -3, 1, 2, because I was looking at 3 here. I was like, oh, you can do 3 and 1 and 2, but these aren't negative, or I guess their signs aren't flipped. So there's nothing more than one solution. So yeah, how would you avoid the duplicates?
We're going to add that again to our result set, right? But that's not what we want.
Don't do
we
that.
want to eliminate
Don't do
the
that.
duplicates. So the problem was we took -3 as our A value, right? And then we searched the rest of the array for two numbers, 1 and 2, that add to 0. But then we went back here, right? And we found the -3 again, and we did the exact same thing. The problem is we don't want to have the same number in this position, in the A position, twice, because then if there are the numbers that come after it, we could potentially find duplicates. The solution to this problem is to sort the input array. Let me show you what I mean. So here you can see that the array is now sorted. Let's cross out our top array, which was unsorted. So now we are going to sort the input array. So now when we're looking for all combinations, if we find -3 first, then that's good. Okay, we'll say -3, then we find these two numbers, 1 plus 2, and then we find our solution. Great. Now if we get to -3 again, we'll say, hey, wait a minute. This number was already in this position, right? And we know that because its neighbor, its left neighbor, is the same value. We don't want to put it twice here, because if we do, we'll get the same duplicate.
Okay, I got
Let
lost
me show you what I mean. So here you can see that the array is now sorted. Let's cross out our top array, which was unsorted. So now we are going to sort the input array.
Oh, that's
so
what I didn't
when
understand.
We're looking for all
that's what I missed on my.
If we find negative,
that's what I missed when I was looking through the writing out here. It's like it's sorted at the beginning, but for y.
3 first, then that's good. Okay, we'll say -3, then we find these two numbers, 1 plus 2, and then we find our solution. Great. Now if we get to -3 again, we'll say, hey, wait a minute. This number was already in this position, right? And we know that because its neighbor, its left neighbor, is the same value. We don't.
So that's why you look at this. If index is greater than 0 and num's index equals num's index minus 1, then you continue. Because you're checking if this is the same as the previous value, so you can avoid duplicates. And because the first however many values of the array will be negative because you sorted them, you can make sure that you don't go past these negative values with this initial index, num's index. So if num's index is greater than 0, my bad, sorry about that, then you can say that you're no longer qualified to keep looping through the array.
Don't want to put it twice here, because if we do, we'll get the same duplicate. So we're going to tell ourselves that we already computed all combinations that start with a -3, so we don't need to do that anymore. We already visited this one, we're going to skip this one, and then we're going to go here. So that means in this case, we're not going to find any more results in the remaining portion of the array because they're all positive. They're never going to sum to 0. So then in our result, we're only going to have the one triplet, -3, 1, and 2. We eliminated duplicates by not reusing the same element twice.
That makes a lot of sense.
I think it helps to understand a little bit about the statistics of like combinations and permutations to like understand exactly why this eliminates duplicates. But I hope this explanation at least helped a little bit. So now that we know to sort the input array and we know how to eliminate duplicates, once we find our first number, notice, right? So let's say we have a -3. So then the remaining part of the problem, there's only 2 elements, right? So it basically reduces to 2-sum. And you probably know how to solve 2-sum, right? Obviously.
Oh, that's crazy. What? Holy shit. Sorry for cursing. Oh my god. Are you serious? So it's like you're finding a target at the beginning with the negative number, and then you use 2-sum to find the the elements that add up to the target.
You can put the numbers, let's say that this is our first A, right? So then for the remaining portion, we're basically going to do 2-sum. And you can do that with a hash map or a hash set. But if you've solved the problem 2-sum 2, you know that we don't need to use a hash map.
Yo, but you can use the 2 pointers.
We can use a left and right pointer. So this is our left, and this is our right. And
oh, what the heck? What am I doing? I messed up that part about having the array sorted. So you're still looking at these, right? Does that make sense? Am I insane? You're only looking at negative values? Is that right for the first value?
if we find numbers
No, that doesn't. That's not right.
left and right added to our -3 sum to 0, then we're going to add them to the solution set.
Can this be negative?
If the sum, though, is too big, for example, if our sum was greater than 0, we want to decrease our sum. Now, we can do that by taking our right pointer and shifting.
Oh, that's what I'm saying. If nums left and nums right is less than 0, minus nums index, left is +1. So this means that left +1, this means that the leftmost value is still negative.
At. So our right pointer would be shifted here. Notice how that decreases the sum because the numbers are sorted. So if you've solved 2-sum 2 before, you know exactly why this works. And I encourage you to watch that video if you want a deeper explanation. Now, on the other hand, maybe our sum is too small. Our sum.
I need to review 2-sum again, that 2-sum 2 again, because I don't quite I can't quite wrap my brain around this pointer business yet and be able to explain that from the basic constituent parts.
Is smaller than 0, in that case we would shift our left pointer.
But I recognize the pattern.
Because the input array is sorted, if we shift our left pointer, we're increasing the sum. Now, there could be duplicates among these left and right values too. For example, if this 1 was a -3 instead, right? In that case, we don't want to reuse the same element twice, even among our left and right values. So we would not use the same, we would shift our pointer once more over here. We don't want to reuse the same value for left and right either, so we don't get any duplicates. Now, in terms of time complexity, remember we are sorting the array, which is big O of n log n. And then we are not doing the brute force with triple loops. That would be n cubed. We are using the fact that this input array is sorted to our advantage.
Puke all over the screen.
We're using one loop to tell us the first value, and we're using the second loop to basically solve 2-sum. So we're going to have 2 nested loops, and that's going to give us O n squared. So that means, obviously, the time complexity reduces to just O of n squared. Now, the space complexity will depend. So for the implementation I'm showing, it could be big O of 1, or it could be big O of n.
I like how space complexity is starting to come to me as a concept.
Sorting actually does take extra memory in some libraries, so it depends on your implementation of sorting. It could be O of n. Okay, now let's get to the code. So we remember we have to, what we want to do is sort index and the value. And remember, we don't want to reuse the same value in the same position twice. So if I is greater than 0, meaning this isn't the first value in the input array, and this value a is equal to nums of I minus 1, that means it's the same value as before. That means we want to continue. We don't want to reuse the same value twice. So we're going to continue to the next iteration of the loop. Next, we're going to use our 2-pointer solution for the remaining portion of the array to basically solve 2-sum. So we'll have left and right pointers. Left will initially be I plus 1 to num right, oh, 2. And remember, we don't want to reuse the same value in the same position twice. So if I is greater than 0, meaning this isn't the first value in the input array, and this value a is equal to nums of I minus 1, that means it's the same value as before. That means we want to continue. We don't want to reuse the same value twice. So we're going to continue to the next iteration of the loop. Next, we're going to use our two-pointer solution for the remaining portion of the array to basically solve two-sum. So we'll have left and right pointers. Left will initially be I plus 1. Right will be the end of the list.
I think there needs to be some kind of updated threesome.
Left, if it's greater than 0, which is what we're looking for, then we need to decrease it, in which case we would say our right pointer needs to be decremented. On the other hand, if it's too small, we need to make the sum bigger. If only I could type
I'm starting
today.
to get lost in this. I'll have to revisit this one.
Okay, now let's get as a list of lists. And remember, we don't want to reuse the same value in the same position twice. So if I is greater than 0, meaning this isn't the first value in the input array, and this value a is equal to nums of I minus 1, that means it's the same value as before. That means we want to continue. We don't want to reuse the same value twice. So we're going to continue to the next iteration of the loop. Next, we're going to use our two-pointer solution for the remaining portion of the array to basically solve two-sum. So we'll have left and right pointers. Left will initially be I plus 1. Right will be the end of the list. Length minus 1. Left and right can't be equal, so we're going to say left is less than right. Now we're going to actually compute the sums. So we'll say our threesum is a plus nums of left plus nums of right. So
which is the value and nums of less and nums of right.
Is too great, remember. If it's greater than 0, which is what we're looking for, then we need to decrease it, in which case we would say our right pointer needs to be decremented. On the other hand, if it's too small, we need to make the sum bigger. If only I could type today. If it's too small, we need to make it bigger, so shift our left pointer to the right.
Oh wow, that's interesting how you can control the size of the pointer or the size of the sum by shifting the pointers because the values are sorted.
If this is equal to 0, so of course we have to add it to our result. So to our result, we're going to append all three numbers. So the numbers are a, nums of left, and nums of right. Now, so of course, we got to update our pointers, but how do we update it? There's a lot of ways you can do it, but I'm going to show you the way that you can do it with writing the minimal amount of code. So let me just write a comment to show you a little bit. What if we had the two-sum basically for these left and right, and we were at -2, -2, so -2, 0, 0, 2, and 2. What if our left pointer was here and our right pointer was here? In that case, we found a solution, let's say, right? Then we'd want to update our left pointer, right? So then our left pointer gets to -2 again. But that's the same one as before. So in that case, we want to update it one more time to get it over here, right? Now in that case, now our sum is going to be too big because we're going to be at 0 plus 2. So that's greater than 0. So then our loop is going to execute saying that this is too big, and we're going to shift the right pointer to the left. But notice how that right value is now the same as it previously was too, but that's okay because our sum is going to evaluate as too big, so our right pointer is going to be shifted again. Notice how each value is only going to have one corresponding value that it can sum equal to the target, which is 0. So we only have to update one pointer, and our two conditions up here will update the other pointer by itself. We don't even have to worry about it. So in this case, we're only going to shift our...
That's interesting. I hear it. I recognize the pattern, like the instruction, but I don't see it as like a continuous loop in my mind. But if I were to visualize it with VS Code or just seeing how the values change, then I would understand it. So I think I'm going to do that after this.
Our left pointer. If num's of left, that means it's this. Don't want our left pointer to all we need able to just return our result saying that this works on the first try. Let's see. We passed the test case, the first test case.
Excuse me?
They really want you to buy LeetCode Premium. This is taking... Okay, so it did pass. Usually I have some stupid bugs where I mess up a condition, but okay, so we passed it. This is pretty complicated. I'm not going to lie. This is a pretty hard problem to solve if you've only just solved two sum. So I really recommend solving two sum 2 as well before solving this problem. I might have made it look...
He made it look really hard. It's actually a lot easier than he thinks.
easy with the amount of...
Okay, let me plug this into my friend VS Code. So what I want to do is I just want to print index left, right. What? Wow, that's really cool, actually. I like that visualization. So here's nums that's sorted. And we first look at 0, 1, and 5. 0, 1, 5. 0, 1, 5. Then we look 0, 2, 5. 0, 3, 5. 0, 4, 5. Then we go to the next one. 1, 2, 5. Then 1, 3, 4. Then we go to the next one. 3, 4, 5. What? 3, 4, 5. Because it's 1, 2, 3, 4, 5, 6. 0, 1, 2, 3, 4, 5. Then we can also print whenever it appends, because there's a result. We can look 0, 1, 5. Nah, that didn't work. But it's 0, 1, 5. That's not right. Go to the next one. 0, 2, 5. 0, 3, 5. Which is 0, 2, 3, 5. That didn't work. 0, 4, 5. That shouldn't work. What? Oh, but it does the next one because it's 1, 2, 5, which is 1, 2, 5. I just don't understand how the pointers work, like with the indexes. But that's okay. I'm going to figure this out and probably come back to this one.